Jump to content. Main menu. Main menu, move to sidebar, hide. Navigation. Main page, help browse cookbook Wikijunitor feature books recent changes random book using Wikibooks. Community. Reading room forum community portal bulletin board help out. Policies and guidelines contact us. Search. Search. Appearance. Donations create account login. Personal tools. Donations create account login. Pages for Longbout editors learn more. Contributions discussion for this IP address. Contents move to sidebar hide. Beginning. 1 Details. 2 Speed of sound in air. 3 Sound in solids. 4 Experimental methods toggle experimental methods subsection 4.1 single shot timing methods. 4.2 Other methods. 5 External links. Toggle the table of contents. Acoustics/sound speed. Add languages. Add links. Book discussion. English. Read edit source viewed history. Tools. Tools move to sidebar hide. Actions. Read edit source viewed history. General. What links here related changes upload file special pages permanent link page information site this page gets shortened URL download QR code. Sister projects. Wikipedia Wikiversity Wiktionary Wikiquote Wikisource Wikinews Wikipedia Commons Wikidata Media Wiki MetaWiki. Print/export. Create a collection download as PDF printable version. In other projects. Wikidata item. Appearance move to sidebar hide. From Wikibooks, open books for an open world. Acoustics. The speed of sound C from Latin celeritas. Velocity varies depending on the medium through which the sound waves pass. It is usually quoted in describing properties of substances e.g. sodium's speed of sound is listed under other properties. In conventional use and scientific literature, sound velocity v is the same as sound speed c. Sound velocity c or velocity of sound should not be confused with sound particle velocity v, which is the velocity of the individual particles. More commonly the term refers to the speed of sound in air. The speed varies depending on atmospheric conditions. The most important factor is the temperature. Humidity has very little effect on the speed of sound, while the static sound pressure air pressure has none. Sound travels slower with an increased altitude elevation if you are on solid earth primarily as a result of temperature and humidity changes. An approximate speed in meters per second can be calculated from CIR equals 331. 5 plus 0. 6m/s \display style c_mathream air equals 331.5 plus 0.6 /c.data /mathream where display style data theta is the temperature in degrees Celsius. Details edit vertical line edit source. The more accurate expression for the speed of sound is C equals RT display style C equals /SQRT kappa C dot R C dot T where R is the gas constant 287.05 joules/kilograms K for air. It is derived by dividing the universal gas constant R display style RJ/mole K by the molar mass of air kilograms/mole as is common practice in aerodynamics. Kappa is the adiabatic index 1.402 for air sometimes noted as gamma. T is the absolute temperature in kelvins. In the standard atmosphere, T0 is 273.15 K equals 0 degrees C equals 32 degrees F giving a value of 331.5 meters/s equals 1087.6 feet/s equals 1193 kilometers/h equals 741.5 miles per hour equals 643.9 knots. T20 is 293.15 K equals 20 degrees C equals 68 degrees F giving a value of 343.4 meters/s equals 1126.6 feet/s equals 1236 kilometers/h equals 768.2 miles per hour equals 667.1 knots. T25 is 298.15 K equals 25 degrees C equals 77 degrees F, giving a value of 346.3 meters / S equals 1136.2 feet / S equals 1246 kilometers / H equals 774.7 miles per hour equals 672.7 knots. In fact, assuming an ideal gas, the speed of sound c depends on temperature only, not on the pressure. There is almost an ideal gas. The temperature of the air varies with altitude, giving the following variations in the speed of sound using the standard atmosphere. Actual conditions may vary. Any qualification of the speed of sound being at sea level is also irrelevant. Speed of sound varies with altitude height only because of the changing temperature. Altitude temperature m/s kilometers /h mph knots. Sea level 15 degrees C 59 degrees F 340 12 25 761 661 11,000 meters 20,000 m cruising altitude of commercial jets, and first supersonic flight -57 degrees C -70 degrees F 295 1060 to 660 573 29,000 meters flight of X-43A -48 degrees C -53 degrees F 301 1083 673 585. In a non-dispersive medium, sound speed is independent of frequency. Therefore the speed of energy transport and sound propagation are the same. For audio sound range, there is a non-dispersive medium. We should also note that air contains CO2, which is a dispersive medium, and it introduces dispersion to air at ultrasound frequencies ~28 kHz. In a dispersive medium, sound speed is a function of frequency. The spatial and temporal distribution of a propagating disturbance will continually change. Each frequency component propagates at its own phase speed, while the energy of the disturbance propagates at the group velocity. Water is an example of a dispersive medium. In general, the speed of sound c is given by c equals c \displaystyle c equals \sqrd \frac c \rho, where c is a coefficient of stiffness \displaystyle \rho is the density. Thus the speed of sound increases with the stiffness of the material, and decreases with the density. In a fluid the only non-zero stiffness is to volumetric deformation. A fluid does not sustain shear forces. Hence the speed of sound in a fluid is given by c equals k \displaystyle c equals \sqrd \frac k \rho, where k is the adiabatic bulk modulus for a gas. K is approximately given by k equals p \displaystyle k equals \kappa c dot p, where is the adiabatic index, sometimes called p is the pressure. Thus, for a gas the speed of sound can be calculated using c equals p \displaystyle c equals \sqrd \kappa c dot p over \rho, which using the ideal gas law is identical to c equals rt \displaystyle c equals \sqrd kappa c dot r c dot t. Newton famously considered the speed of sound before most of the development of thermodynamics, and so incorrectly used isothermal calculations instead of adiabatic. His result was missing the factor of but was otherwise correct. In a solid, there is a non-zero stiffness both for volumetric and shear deformations. Hence, in a solid it is possible to generate sound waves with different velocities dependent on the deformation mode. In a solid rod with thickness much smaller than the wavelength the speed of sound is given by c equals c \displaystyle c equals \sqrd frac e \rho, where E is Young's modulus \displaystyle \rho is density. Thus in steel the speed of sound is approximately 5100 meters /s. In a solid with lateral dimensions much larger than the wavelength, the sound velocity is higher. It is found by replacing Young's modulus with the plane wave modulus, which can be expressed in terms of the Young's modulus and Poisson's ratio as m equals e1, 1 to 2 \displaystyle m equals e \frac 1 \nu to \nu circumflex accent 2 for air. See density of air. The speed of sound in water is of interest to those mapping the ocean floor. In salt water, sound travels at about 1500 meters /s, and in fresh water 1435 meters /s. These speeds vary due to pressure, depth, temperature, salinity and other factors. For general equations of state, if classical mechanics are used, the speed of sound C is given by C2 equals P C circumflex accent to equals frac partial P partial rho, where differentiation is taken with respect to adiabatic change. If relativistic effects are important, the speed of sound S is given by S2 equals C2PE vertical line and diabeta TIC S circumflex accent to equals C circumflex accent to left dot frac partial P partially right vertical line underscore or adiabatic note that E equals C2 plus EC E equals rho C circumflex accent 2 plus E circumflex accent C is the relativistic internal energy density. This formula differs from the classical case in that rho has been replaced by E/C2 E/C circumflex accent to speed of sound in air edit vertical line edit source impact of temperature in degrees cc in m/s in kilograms/m superscript 3 z in n/s/m superscript 3 negative 10 325.41.341 436.5 negative 5 328.51.316 432.4 0 331.51.293 428.3 plus 5 334.51.269 424.5 plus 10 337.51.247 420.7 plus 15 340.51.225 417.0 plus 2343.41.20 for 413.5 plus 25 346.31.184 410.0 plus 3349.21.16 for 406.6. Mach number is the ratio of the object's speed to the speed of sound in air medium. Sound in solids edit vertical line edit source. In solids, the velocity of sound depends on density of the material, not its temperature. Solid materials, such as steel, conduct sound much faster than air. Experimental methods edit vertical line edit source. In air, a range of different methods exist for the measurement of sound. Single-shot timing methods edit vertical line edit source. The simplest concept is the measurement made using two microphones and a fast recording device such as a digital storage scope. This method uses the following idea. If a sound source and two microphones are arranged in a straight line, with the sound source at one end, then the following can be measured. The distance between the microphones x, the time delay between the signal reaching the different microphones t, then v equals x/t. An older method is to create the sound at one end of a field with an object that can be seen to move when it creates the sound. When the observer sees the sound-creating device act, they start the stopwatch, and when the observer hears the sound, they stop their stopwatch. Again, using v equals x/t, you can calculate the speed of sound. A separation of at least 200 meters between the two experimental parties is required for good results with this method. Other methods edit vertical line edit source. In these methods, the time measurement has been replaced by a measurement of the inverse of time frequency. Kud's tube is an example of an experiment which can be used to measure the speed of sound in a small volume. It has the advantage of being able to measure the speed of sound in any gas. This method uses a powder to make the nodes and antinodes visible to the human eye. This is an example of a compact experimental setup. A tuning fork can be held near the mouth of a long pipe which is dipping into a barrel of water. In this system, it is the case that the pipe can be brought to resonance if the length of the air column in the pipe is equal to 1 plus 2n/, where n is an integer. As the antinodal point for the pipe at the open end is slightly outside the mouth of the pipe, it is best to find 2 or more points of resonance and then measure half the wavelength between these. Here it is the case that v equals f. External links edit vertical line edit source. Calculation. Speed of sound in air and the temperature. The speed of sound, the temperature, and not the air pressure properties of the U.S. Standard Atmosphere 1976 Fundamentals of Psychoacoustics Filter Design and Implementation. Fundamentals of Psychoacoustics Acoustics Filter Design and Implementation. Retrieved from https://w/index.php title equals acoustics/sound_speed and bolded equals 3,759,396. Category: Book: Acoustics. This page was last edited on November 3, 2020, at 2000 hours. Text is available under the Creative Commons Attribution Share Alike license. Additional terms may apply. By using this site, you agree to the terms of use and privacy policy. Privacy policy about Wikibooks. Disclaimers. Code of conduct. Developers. Statistics. Cookie statement. Mobile view.